Did about the Fourier transform expression and the inverse Fourier transform expression at here. Let's look at the delta function expression. From here, the xj omega are given this one. If I plot with xj omega at here, okay, xj omega is a 2 pi times delta function. At the omega 0, it's a delta function. 2 pi times delta omega minus omega 0. Okay, this one is spectral domain. In the spectral domain, it's a delta function like that. Take an inverse Fourier transform. You can refer to this expression. It's a 1 over 2 pi, and taking integration range minus infinity to infinity, and xj omega is this part. This one is xj omega, and the basis function, and taking the omega. The omega changing minus infinity to the infinity. Okay, then 2 pi and 2 pi we cancel out, and delta function integration just to replace for the non-zero omega. At this moment, omega should be omega 0. All the other omega are 0. So omega are replaced by omega 0. That becomes this one. So it means that the inverse Fourier transform of this one is e to the j omega 0 t. Okay. Then Fourier transform of this one are this one. So this one is a Fourier transform pair. Okay. So by taking inverse Fourier transform of this 2 pi delta omega minus omega 0 are given e to the j omega t. It means that the e to the j omega 0 t Fourier transform will be 2 pi times delta, okay, 2 pi times delta omega minus omega 0. Okay, keep in mind that these relationships, we prove that one. Inverse Fourier transform are given this one. Inverse Fourier transform. These relationships. Okay, what about this Fourier transform? In this case, cosine omega 0 t are e to the j omega 0 t plus e to the minus j omega t. Okay, e to the minus j omega 0 t divided by 2. Okay, this is cosine omega 0 t. By taking Fourier transform, we know that each of these one is delta function and divided by 2. So divided by 2 is it cancel out that one. So it will 2 pi delta omega minus omega 0 and the plus 2 pi delta omega plus omega 0. So it looks like this one. Pi times delta omega minus omega 0 and plus pi times delta omega plus omega 0. So we can plot this one in the spectral domain like that one. This one is 0 point, and omega 0, it has pi delta omega minus omega 0 is this term, and this one is minus omega 0. Spectral competence is pi times delta omega plus omega 0. You need to keep in mind the delta function, this argument should be 0 to have non-zero value. So omega equals to omega 0, it has non-zero value. In this case, omega equals to minus omega 0, it has non-zero value. So spectral domain, it can be expressed in this way. In the time domain, it's a cosine. Okay, so the same signal can be expressed in the time domain. It looks like this one. This one is cosine t equals 0. In the time domain, it looks like this one, but in the frequency domain, it looks like that one in the omega axis. Similarly, you can do for the sine. sine is e to the j omega t minus e to the j minus t divided by 2j. In that case, you can figure out the relationship between the sine and the delta functions. And this one is another comment for the Fourier transform. Usually the Fourier transform is complex number. Okay, complex number can be expressed by its magnitude and the phase. So the complex number x j omega, it has magnitude and angle, or we can express that one the same thing in this way: complex exponential functions. So magnitude and angle are usually used in the to plot or express the Fourier transform function. Here is another comment: if xt is a real number, like this cosine. So cosine or sine, it has the positive frequency and negative frequency are complex conjugate. You can see here, sine function is also a real number. So this one and this one, compare that one, it's a complex conjugate one. This one is a positive frequency component, this one is a negative frequency component. Both of them should be complex conjugate. As we know that the e to the j omega 0 t, this one is positive frequency component if it has the complex number of c1, then c minus 1 is when we think about Fourier series coefficient, this one is minus j omega 0t. Then if c minus 1 and c1 is complex conjugate, then complex conjugate adding each other, that will give the real number. So due to that one, xt is a real valued signal, then negative frequency component is should be complex conjugate of a corresponding positive frequency. So left hand, the negative frequency component and positive frequency component are related by the complex conjugate. This one says that Hermitian symmetry. So it should be satisfied to become the time domain signal real number value. And if it satisfies these conditions, then positive frequency the component and negative frequency component magnitude is the same. Okay, magnitude should be the same. It means that the magnitude is even function, but the phase terms, complex term is the opposite number by the conjugate. So the angle should be other function of omega. So this is the whole things. So it means that the characteristic of a Fourier transform for real signal. In real signal, positive and negative frequency components are related as a complex conjugate. If it satisfies these complex conjugate conditions, then magnitude is even function of omega, but the phase is other function of omega. It should be satisfied that one. This one is another story. Analytic signal like this one, if xt has any spectral domain like this one, a positive frequency is this one, I plotted xj omega. Okay, and the negative frequency domain has this one. In these cases, negative frequency component cannot be complex conjugate of positive frequency spectrum. So in this case, the signal is not real number, it's a complex number. Anyway, it is real or complex. If we can calculate this one, this signal function is this one. If omega is positive, it is 1. If omega is negative, it's minus 1. Okay. If omega equals 0, it's 0. This is a signal function, sine function. So sine function definition is this one. If the argument is positive, it's 1. Argument is negative, then it's minus 1. If argument is 0, it's 0. If we adding this spectral component, if positive frequency cases, it's the same. But the negative frequency component due to this sine function, this becomes negative sign. So by adding this one, negative frequency component is cancelled out. So if positive frequency case, omega is positive, then it's doubled. Okay, doubled. But if frequency is negative, it's cancelled out. Only positive spectral component are remained. What about DC component? In case of DC component, omega equals 0, then this goes to 0. So only the omega remain. This is DC component. Okay, this is called Hilbert transforms. Hilbert transform, we can cut out the left hand or negative frequency component. If reverting that one, we can remove the positive spectral component. So we can remove one of the frequency side by use of these Hilbert transforms. We talk about the deleted conditions for the Fourier series. It's similar to exist for the Fourier transform. This integral should be exist. To exist this one, it means that the integration value should be finite. So in absolute integrable means this one. This one is a Fourier transform of xt. The absolute value of this one is always less than or equal for the absolute value of this one. You know what? Magnitude of this one is 1. So internal magnitude will give this one. If it is a finite, then automatically xj omega is integrable. So for the existence of the Fourier transform, xt should be absolutely integrable. That's this one. Xt is absolutely integrable, then Fourier transforms exist. Deleted conditions is the same as Fourier series expansion existence. Xt should be absolutely integrable. That's this one. The next one is xt has a finite number of maxima and minimum within any finite interval. And xt should be a finite number of discontinuity when any given finite interval. We talk about this one in the Fourier series, so I would like to skip at this moment, but you need to refer the Fourier series coefficient when we talk about the deleted conditions. This one says that the existence of Fourier transforms, but most of the cases we are handling the signal satisfy these conditions. Here shows an example rectangular pulse. We already talked about this one, so this should be positive. It is 0 all the way 0 except this period. Magnitude is a. At this moment is a, and this time is tau. Okay. Then taking the Fourier transform, you know that xt is non-zero only between this time period, and in this period xt is a, so this is the a, and this one is complex exponential taking integration over t. Okay, then it will give these expressions. Replace the t with the integral range tau over 2 and minus tau over 2, then it will give this one. So rectangular pulse amplitude is a and time span is tau. Then Fourier transform expression is a tau times sinc f tau. Okay, a tau sinc f tau. Okay, think about this one. The a tau is the area of this one. As I talked to you that if this argument goes to the 0, then sinc function should be 1. Okay, f is 0, then this should be 1. So let's say this one is frequency f, and if you multiply 2 pi, then this becomes the omega 2 pi f. So frequency axis can be taking the omega or f. The low bound is taking the f, the upper side I refer to the omega. At the DC component, f is 0. Okay, f is 0. In that case, it's a tau. Okay, it's peak value is a tau. This peak value corresponding to this area of this rectangular pulse. And what about the first null? First null is a 1 over time period, tau, 1 over tau, okay, 1 over tau. So this period is tau. So taking inverse of that, that gives the first null frequency. What about in the omega domain? Omega domain is just multiply 2 pi. So this becomes a 2 pi over tau angular frequency. We call omega as angular frequency. But f is just the frequency. Okay. In the spectral domain, we can refer f, or you can refer the angular frequency, whatever. Okay. So the Fourier transform of rectangular pulse are given like this one. This one is obviously minus 1 over tau. So this one is a first null point. So think about at the DC component, a tau is the area of this one, and the first null can be found from the inverse of the pulse width. At this moment, pulse width is tau, so that's this tau. Okay, this is the same. Here shows that the magnitude response of this one by taking the absolute value of this one. The magnitude is a tau. First null is this one, and you know that this part is negative, but this one is a positive period. So negative period, the angle is minus pi or pi. Conventionally, as the frequency increase, the angle is decreasing. When we talk about the time shifting, say omega 0 TD. As frequency increasing, the angle is decreasing. So we will talk about when we consider the time shifting. Conventionally, angle is decreasing as frequency increasing. So we're taking the pi at the negative frequency and the positive frequency is minus pi. At here, you know what this one is plotted xj omega with the magnitude and angle simultaneously. But at here, we plotted the magnitude at here, j omega. Okay, so as we know that this one is a real signal, so xj omega magnitude should be symmetric. It's even function. And what about the phase of the xj omega? Phase is a positive. It means a zero angle. This one is a minus pi. This should be pi. This is 0, 0 like that. It's repeated pi, 0, minus pi, 0. That's the impedance. You know that this was 1 over tau, minus 1 over tau frequency. 1 over tau. This one is 1 over tau. So during this frequency range, the angle is 0. But this frequency range, this is 1 over tau, this is 2 over tau. Okay? Between 1 over tau and 2 over tau frequency, it's a minus pi. This is 2 over tau. Okay? And the 2 over tau and 3 over tau is a positive frequency. So this is the angle is 0 because this is positive. So we can plot the x j omega is a magnitude and phase simultaneously like this one, or we can plot that one magnitude and the phase. In the magnitude is even function, but the phase function is odd functions. Okay. Magnitude plot can be done by use of dB scale. We are taking the 20 times log 10 absolute value of xj omega is the dB scale plot. So this corresponding to the first null. I can show you that that one over here. Okay, I can hold off. And another figure. I would like to plot the sinc function. 20 times log 10 xs. Okay, this just plot the sinc function. Okay, the range is too large, so I need to change the range of the axis, and x will plot it -5 starting and end 5, and y range is too large, so I just 50 to 10. Okay, -50 to 10 is the y range maximum. So by use of this constraint, let's plot that again. Okay, now it gives this kind of pattern. Okay, so this one is a log scale. The same thing can be plotted in magnitudes can be plotted in this way, but if you're taking log, it looks like this one. But here, think about this one is a 1 taking, you know that the log 1 is 0 dB, so this is 0 dB. Okay, I think this is better to understand. Okay, let's try it again. Okay, so this point corresponding to this one, 0 dB, and think about what it will be this first node difference maximum point. Okay, from here to here ratio. Okay, from here to here, that's not that big. So I mean, this one is this difference is what is okay. To find out this value, okay, I mean that what will be this value? We know that this one is 1. What about this one? As we talk about sinc function, the global maximum is here. It's at 0, this point, and this one is null. Next maximum point is this point. This point is 1.5. If t equals to 1.5, then the value will look like this one, sine pi plus pi over 2 divided by pi times 1.5. So when we taking this value 1.5, then it will give pi times 1.5 over -1. We know that this is -1, but taking the absolute value of this one will give 1 over pi divided by 1.5. So this is the this value. Okay, then by taking the dB scale 20 times log 10 0.2122. Okay, this one is minus 13.45, 13.5. That's the dB scale value of this one. This is property of sinc functions. Okay, we talk about Fourier transform of rectangular pulse. The amplitude is A, and the time width is tau. By taking the Fourier transform, it looks like this one. And we can plot the Fourier transform magnitude and phase simultaneously, like this way. And the first null occurred at the 1 over tau or minus 1 over tau, and DC component corresponding to the area of this pulse. And every integer multiple of 1 over tau becomes the 0. Okay, negative is the same. Integer multiple of this one is 0 and 0 and 0. This one also 0, 0, 0, like that. And also we can plot this one magnitude and angle patterns. Basically this one is a complex number, but at this moment it is a positive or negative only. So this one, it seems like a real number, but there is some time shift exists, then this becomes the complex number. So in general, we can plot the Fourier transform magnitude and angle ways, but the real signal cases, magnitude should be even function of omega, but the phase should be other function. And sometimes we plot the magnitude in the dB scale. Then it looks like this one. In case of sinc function, the first null depth is a minus 13.5 dB difference. So other pulse shape has different value of this one. Next example is exponential function. Here is a exponential function. It's a right-hand sided signal. It means that this is t multiplied ut, then signal only exists at the positive time. And we think about this a is a positive, then the signal pattern will look like you know that because of the unit step function all the way 0 at t equal less than 0 cases, but at t equal 0 it becomes the 1. Okay, and after that, because a is positive, it goes decaying like that all the way down. So we would like to take a Fourier transform of this pattern. Okay, then it can be obtained by taking integration minus infinity to infinity, but the negative time is 0. So we can starting from 0 to the infinity. During this positive time, xt is e to the minus at. And the basis function is e to the minus j omega t, and taking integration, okay, dt. This is type 4. Then you know that this product will give e to the minus a plus j omega times t, and we need to take integration this one over 0 to the infinity. Then the integration will given like this when integration ranges 0 to the infinity. When we take infinity, because a is positive, it should be 0. And in case of t equals 0, this becomes the 1. That's why it becomes this value. So Fourier transform of exponential function of this one is given 1 over a plus j omega. When we plot this one, you know that this one is complex number. We can plot that one magnitude and phase. Magnitude can be found from these relationships. We can plot the this magnitude with respect to omega. It's shown here. We can plot this one magnitude versus omega. Okay, then we can get this value. And when the omega are equals to a, then this value becomes the 1 over a times 1 over square root 2. Okay, when omega is a or minus a, plus minus a, okay, plus a or minus a, this becomes 1 over a times square root 2. 1 over square root 2. And this peak value, you know that omega equals 0, it's 1 over a. Okay, this is the magnitude plot. As we know that by the square, it is an even function of omega. Okay, what about the phase response? Phase response is the real and imaginary are a and omega, so it's arctangent of omega over a. Then we can plot that one in this way. And omega equals to 0, it's angle 0. But omega is larger, it goes to the negative phase. As omega goes to the infinity, it approaches to the 90 degree, minus pi of 2. But in the negative infinity cases, it goes to the pi over 2. This one is a 90 degree and minus 90 degree. That's the function of arctangent. What about omega equals to a? In this point, it's a pi over 4. Omega equals to a, then arctangent 1 is a 45 degree. Okay, omega equals to 1. It means that the tangent 45 pi over 4 I equals to 1. So this one means the omega over a. And similarly, in the plus a, it is also minus pi over 4. Okay. This one shows that the Fourier transform result of exponential function.